Hello everybody. In this chapter we will be looking at different refrigeration cycles. A major application area of thermodynamics is refrigeration, which is the transfer of heat from a lower temperature region to a higher temperature one. Devices that produce refrigeration are called as refrigerators, and the cycles on which they operate are called as refrigeration cycles. Most frequently used refrigeration cycle is the vapor compression refrigeration cycle, in which the refrigerant is vaporized and condensed alternatively and is compressed in the vapor phase. Another well-known refrigeration cycle is the gas refrigeration cycle, which is in which the refrigerant remains in the gaseous phase throughout the cycle. Other refrigeration cycles discussed in this chapter are cascade refrigeration, where more than one refrigeration cycle is used, and absorption refrigeration, where the refrigerant is dissolved in a liquid before it is compressed. So in this chapter, we will introduce the concepts of refrigerators and heat pumps and measure their performances and analyze the ideal vapor compression refrigeration cycle. We'll also analyze the actual vapor compression refrigeration cycle. We'll review the factors involved in selecting the right refrigerant for an application and discuss the operation of refrigeration and heat pump systems. We'll also evaluate the performance of innovative vapor compression refrigeration systems and also analyze gas refrigeration systems. And finally, we will introduce the concepts of absorption refrigeration system at the end of the chapter. We all know from experience that heat flows in the direction of decreasing temperature, that is, from a higher temperature region to a lower temperature one. This heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. The transfer of heat from a low temperature region to a high temperature one requires special devices called as refrigerators. Refrigerators are cyclic devices, and the working fluids used in refrigeration cycles are called as refrigerants. A refrigerator is known schematically in figure 11-1a here, where Q sub L is the magnitude of the heat removed from the refrigerated space at temperature T sub L. Q sub L is the magnitude of the heat rejected to the warm space at temperature T sub H, and W net in is the network input to the refrigerator. It should be noted that Q sub L and Q sub H represents magnitudes and as a result are positive quantities. Another device that transfers heat from a low temperature medium to a high temperature one is called the heat pump. Refrigerators and heat pumps are essentially the same devices. They differ in their objectives only. The objective of a refrigerator is to maintain the refrigerated space at a lower temperature by removing heat from it. Discharging this heat to a high temperature medium is merely a necessary part of the operation, although it is not the purpose. The objective of a heat pump, however, is to maintain a heated space at a high temperature. This is accomplished by absorbing heat from a low temperature source such as well water or cold outside air in winter and supplying this heat to a warmer medium such as a house. A figure of the heat pump is given in figure 11-1b. The performance of refrigerators and heat pumps is expressed in terms of the coefficient of performance or COP, and the COP of refrigeration is defined as the desired output divided by the desired input, which is going to be equal to the cooling effect divided by the work input, which also would equate to Q sub L divided by W net in, work net in. And the coefficient of performance of a heat pump, COP sub HP, would be equal to the desired output divided by the required input, and also would be equal to the heating effect divided by the work input, which would equate to Q sub H divided by work net in, or the net work input. These relations can also be expressed in the rate form by replacing the quantities Q sub L, Q sub H and W net in with Q dot L, Q dot H and W dot net in. Notice that both COPR and COPHP can be greater than 1. And also a comparison of above equations reveals that COPHP would be equal to COP sub R plus 1 for fixed values of Q sub L and Q sub H. This relation implies that COP of a heat pump would be greater than 1 since COP of refrigeration is a positive quantity. That is, a heat pump functions at worst as a resistance heater, supplying as much energy to the house as it consumes. In reality, however, part of Q sub H is lost to the outside air through piping and other devices, and COPHP may drop below unity when the outside air temperature is too low. When this happens, the system normally switches to the fuel or natural gas, propane, oil like that, or the resistance heating mode.